Hey everyone, in this video we're going to talk about estimating runtime complexity. We're going to look at 3 different Python code samples and evaluate their effect on how, as input grows, the complexity grows. When you ever heard of big O notation, what we're really just talking about is counting or estimating the number of operations it will take to deal with the input, and then kind of plotting how that grows as the input size grows. The fundamental question here is we're trying to figure out, how does this algorithm scale? It might work pretty well with a pretty small input, but if it gets to be much larger than the original tested input, sometimes an algorithm can be like really horrible, as you can see in this like horrible zone up here. It's really hard to scale algorithms that operate like this. Algorithms that operate like this are sometimes okay, but usually you want them to end up like this, otherwise they can't handle very large inputs. Okay, so let's look at a couple of different Python code examples. We've got this one that prints the very first item from an array. We've got this one that looks over all of the elements in an array. And then we've got this one that looks over all of the elements in an array and prints them next to all of the other elements in that same array. And we'll be able to look at kind of how that grows. And so let's take a look at the first one in order to do that. Python Tutor can help you a lot as you're visualizing this, and so if you have written some code and you want to know what's the big O, I've kind of created this little sheet here, and I'll copy it and send it out to everyone so that you can kind of add your things there and you can see how it grows. Really, we're just looking at input over execution steps, and that's a good way to kind of talk about how an algorithm grows over time, or over input. So let's look at print first item. We've got 3 arrays. We've got 1 through 3, 1 through 6, and then 1 through 12. So let's see, how long does that take? So we allocate all of those arrays, and then we've got 3 function calls to pass them all through. So let's count the number of execution steps in this function. Okay, we're going to print 1 item, and we're going to print the location at array 0. So that's 2 steps for an input of 3. Okay, I'm going to go over here and just say, okay, that was 2 steps. Now, let's look at when we call it with a twice as large of an array. 1 item, and then we print the first thing. Okay, so that's 2 again. Now, let's do it again for the last one, an array of size 12, so 3 times what our original array was. 1, 2. All right, so what we've seen here is called constant time. You can see it written a lot of times as O of 1, right? Because it doesn't matter how much of an input there is, because it's going to be the same number every time. And so if it's 1 or 10,000, it's all kind of just rounds down to 1, right? So let's call this constant time, right? So when we print all, you might be more familiar with this one, visualize execution. Let's look. So we're going to allocate these 3 lists again and pass the first one into print all items. We've got 1 statement, 2, 3, 4, 5, 6, 7, 8, 9. Okay, cool. So not 9, but 8. Great. I'm going to write that down. So there were 8. We didn't really print all items, we just printed almost all items, right? We stopped at that last one. Alright, so let's go to the next one. So let's see. Print all items. That's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay, now we've gotten up to 14, so I'm going to write that down. 14, cool. Now, let's look at the last one. Twice as large as the last array. Okay. Step 34 of 61, we can kind of see, you know, from here, it's going to be about 25 to 30. Let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26. All right, so 26, right? So this grows pretty predictably with n. As n rises, the number of steps rises by an amount that is the same with each number of steps. It's not in any way larger with respect to the input, right? Maybe you're multiplying the input by 3, right? Maybe there's 3 steps for every 1 element in the input. Maybe you're doing 27 steps for every 1 element in the input. But it doesn't matter as long as it's growing linearly. So this is called O of n, right? Or linear. Okay, so now let's look at print pairs, which prints all of the elements of an array next to all of the other elements of the array. We've got 3, 6, and 12 again. So let's visualize this execution. Okay, that took a second to run. And now let's look at the huge number that we're dealing with here. 1 to 439 steps. So what I'm going to do with Python Tutor is I'm just going to click on these, and that'll kind of show me in the execution down here. You can see like where it's actually happening, right? So I'm just going to fast forward to the first time. Okay, so that's step 5. And then I'm going to try to find, I'm just going to step through it a little bit so you get an idea. No, let's just go back to that first one. Anyway, so you can tell that we go from 5 to 34. So what we're really talking about here is 34 minus 5. So that's 29 steps, just for 1 to 3. 29. Okay. And then you can kind of see here from this second one, calling print all pairs with A2, you can see that it jumps from 34, right, down to 123. So 123 minus 34, well, that's 89 steps in between those two function calls. So I'm going to put that here, 89 steps. Okay, so now let's just fast forward to kind of the end here and see. 123 of 439, so 439 minus 123, 316 steps. Okay, so 316. So what you see here, you can kind of see in this this graph, this line just takes off, right? It looked like this number kind of was pretty high, a lot higher than this like linear time, until we put it next to this other line. We had to add so much more, you know, on the y-axis, because in between the first run with 3 elements, the second run with 89, or with 6 elements, and the third run with 12 elements, we grew from 29 to 316. So it's growing, and it's growing at a predictable pace with respect to the input, but it's growing so much faster than the input that the curve kind of takes off and lifts off away from it, right? And so if we look at this big O algorithm complexity chart, right, you can kind of see like there's that constant line at the bottom, right, O of 1 or O of log n. It just kind of basically rounds down to 0. And then there's O of n up here. There's a little bit of space between. If you kind of think about our graph, it's like out here somewhere, right? And then you've got this one that just takes off, right? This is really O of n times n, right? So it's a little bit faster than O of n. I think it's a little, let's see, n times n is like not in here. But it's a little bit, faster than this, like O of n log n, right? So you can kind of tell that this is going to scale a little bit less well than than our linear time. So this is O of n times n. And we don't actually identify it from the line, right? Like you can kind of see this line curve up, but it's hard to just look at this and then look at that and kind of like match. That's what we're really trying to do. How do we know that this is O of n when this is O of n times n? Let's look at the code. For one, count the for loops. How many for loops operate on the input, right? This one, there's only one for loop. There's no secret other branches in here, so there's no way that this could grow out of control with respect to the input. With this one, you've got two for loops. Now, just because you have two for loops, it doesn't mean that you're O of n times n. But because both of these for loops take as their input the length of the input array, we're going to loop over both of them twice. There's no base case in here. There's nothing that tells us to prematurely cut the loop off short. So we know that this is always going to execute as n times n, this second for loop. So that's how you can tell just by reading the code without kind of making this plot. So yeah, that's kind of how you can look at runtime complexity with different Python statements. So as you're solving these problems and these challenges, try to figure out, most of them are going to be in the like O of n or O of n times n range. Sometimes it's going to be O of n squared. But try to figure out, which one is which. Sometimes there is a constant solution for some of these, or near constant, and so try to identify with your solution what is it operating on, how many times does it operate with respect to the size of the input.